Last meeting, before the election, we discussed about lipids, and what we have learned so far with lipids is that there is no particular structure, that would distinguish it in a similar way that we would distinguish our carbohydrates, with really a repeated formula. For lipids, there is no specific structure. But one common type of lipids is the fatty acids, and we have learned that that is for the simple lipids. That would include fats and waxes. And so the simple one are the fatty acids that we have discussed last time. But there's also that complex lipids, the steroids, other kinds of lipids like the prostaglandins, thromboxanes, and leukotrienes. So we have learned that the fatty acids, the simple one, are the fatty acids, which are hydrocarbon derivatives, and they are actually carboxylic acids that would have the carbon chain rather ranging from starting 4 to 36, but the common actually would have an even number between 12 to 24. No? And this chain can be unbranched and fully saturated. When you say fully saturated, it means that with the hydrocarbon chains, there are no double bonds that we can see. And chain that can contain one or more double bond, we say that our fatty acids are unsaturated. And sometimes you actually see some three-carbon rings or hydroxyl groups or methyl groups also being attached to it. And we have learned that last time, we have the saturated fatty acids like this one. This one is hexadecanoic acid. There's 10 plus 6, that's 16 carbon chain. And the common name for this is palmitic acid. So you can see in the structure, there is C double bond OOH. This is our fatty acid. This is the carboxylic acid. And then you have the hydrophobic end. So in fact, the lipids, the simple fatty acid, has this polar end, and there is this non-polar end, where you have this head and we have this tail. Usually the head is the polar end of the fatty acid, and the tail is the non-polar end of the fatty acid. So a saturated fatty acid such as this is a fatty acid carbon chain lick with all carbon bonds single bonds. So the structural formula for 16 carbon SFP, 16 carbon saturated fatty acid. We have here this formula. The structural formula is usually written in a more condensed form like this one. So for this CH2 is balik-balik. So we just have to indicate the parentheses. And then you have this formula here. Or you can have the zigzag formula for our saturated fatty acid. So balik na siya. Saturated fatty acids, again, there are no double bonds like this in the structure, in the same way that we would define our hydrocarbons to have no double bonds. So we would refer to them as saturated hydrocarbons. So here we have saturated fatty acids with no double bonds. And because of that, you can see from the structure that we can actually pack these fatty acids along with other chains of fatty acids. And with that, there is actually there is a strong interaction with this chain length. So you can see here that the force of interaction between this canina end and the hydrophobic tail could only be due to van der Waals interactions or the hydrophobic interactions. Nevertheless, it could be a strong interaction between them that it would not allow this structure here to move, because there is an interaction in this case, there could be a hydrogen bond interaction or ionic interaction in this case. Now they have the negative end and the hydrogen end here. There would be a hydrogen bond interaction. But in this non-polar end, in this tail, you have this head again, there will be hydrophobic interactions or the van der Waals interactions in this case. And because of that interaction, and this is very, very long, through weeks, even if weak van der Waals interaction, it becomes very, very large, very, very big because of this very long chain length of this hydrophobic end of the saturated fatty acid. It becomes a strong one, and it would not allow this force of interaction, would not allow this fatty acid to move alongside with each other. So in that case, we'd expect our saturated fatty acid to be less fluid. They can't move as freely. No? And because there is this very strong interaction due to the linear, as highly packed organization of this chain of this fatty acid, we expect that this one would have a high melting point. Again, why would have a high melting point? Because of the hydrophobic interactions or the van der Waals interactions in the 5 hydrophobic state. They are particularly highly organized. So because of that strong interaction, they are packed close together. There is a strong interaction due to the van der Waals interactions. They are linear and they are closely packed together. You expect our saturated fatty acids to have a higher melting point, and because of that, they are less fluid. They can't move as freely, okay, and they are likely to be solid at room temperature because of that strong force of interaction. Now, when we try to compare that with unsaturated fatty acids, the unsaturated fatty acids on its carbon chain, hydrocarbon chain, there is one or more double bond that will be present, like this one. This one is cis-9 octadecanoic acid. So there is 10 plus 8 octa, so 18 carbons. You can have here C double bond OOH, and then the 7, 9, 10, 11 plus 7 carbon 8, 9, 10, 17, 18. So you have octadecanoic acid, decene, because you have an ene double bond, and you have on carbon 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. There is this double bond. The cis-9 and cis, which means this, if you remember your organic chemistry, this bulky group here on the same size, we call this one to be cis. Cis-9 octadecanoic acid. But this one is a long name, so there is a common name usually for fatty acid. And we call this one to be oleic acid. You see here in the structure, it's not a straight chain packed, but somewhere in the structure of this unsaturated fatty acid, we call this unsaturated again because of this double bond. And we can see in the structure that it is not linear. Somehow in the chain length, hydrocarbon chain length of this fatty acid, pink cyan or shown, diverge from its structure. Okay. And we'll see later that this one, will affect on the melting point of our unsaturated fatty acid. So a monounsaturated fatty acid, we call this a mono because there is only one carbon double bond that we can see. Okay, in biochemically important monounsaturated fatty acids, the configuration about the double bond nearly is always cis. Usually you can find in unsaturated fatty acids, with respect to the double bond, it will always cis. So different ways of depicting the structure of monounsaturated fatty acids. So you can have this, you can have this one, you can have this. You can write all this carbon so that you have all the dash formula here showing all the carbon hydrogen bond, or you can have the condensed form wherein we can find the CH2 as a repeating unit. So you have CH2, 7. There is 7 of that, and then you have the CH double bond CH. In this case, we don't emphasize on whether the double bond is cis or trans, but you just have to know that the usual configuration for double bond in unsaturated fatty acid, it's cis. Okay, and then you can have the condensed structure again, CH2, 7 carbon, and then the zero one OOH. Or you can use on the zigzag line again, say 1, 2, 3, 4, 5, 6, 7, 8, 9 here, and then you have the double bond. So since this is cis, so you expect again the bulky groups to be on the same side. If this is trans, you expect Panacea, Flipteria. No, this is the cis again structure. So here, this is the, again, the oleic acid, cis 9-octadecenoic acid, this one. You can also indicate our double bond in this manner, no? Or the number of carbons. So 18 colon 1, which means there are 18 carbons, and colon 1 means there's one double bond, and delta 9 means the double bond. Delta superscript 9, it means that the double bond is on carbon 9 relative to this. Okay. What else? So this one is, and here you can see that you don't see the hydrogen here. This one is because normally the carboxylic acid in solution in water will always be dissociated in its ionic form. You've learned that in organic chemistry or in your general chemistry, no? It will be dissociated to its ionic form, wherein you will find the zero bond O minus dissociated plus H plus, no? Because that is an acid. Acid will always dissociate in solution to its ionized form. So you have the deprotonated form of the carboxylic acid minus the hydrogen here. So, and this should have been named the D-cenoate, okay, minus the hydrogen. So here you have the icosapentaenoic acid, or the EPA, okay. You have the 20 carbons, and then there are 5 unsaturated, 5 double bonds, and the double bonds delta is indicated on carbon 5, 8, 11, 14, and 17. So this is carbon 1. You have the 5, 8, 11, 14, and 17. And you will notice that for each double bond, they are in the configuration of the cis, no, oriented in the cis manner. So this is the bulky group. The bulky group, they are on the same side as cis. This is again the bulky group. The bulky group, they are on the same side. Cis, 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 cis. So all these are in cis. Okay. Now there is an old way of, this is the Iupac way of naming our fatty acids or our organic compounds. No, we have to be very specific because the functional group C double bond OOH, no, will always be indicated as carbon number 1. In the old way of system, we have named this one based from the tail, and we call this one as an omega. Okay, for example, here the first carbon, this N will be the omega 1, 1, 2, 3, carbon omega 1, 2, 3, no? And the first appearance of the double bond, we indicated one as omega. So this one, the omega is in carbon 3. So you call this as an omega 3 fatty acid, EPA. Now, if you will look at your mga gatas, your mga some food products, no, they would indicate on their label that they have like omega-3 fatty acids for some claims, no, that it will be beneficial to your system. Okay, I think we have already mentioned this one before. And they have also mentioned on the way to name our fatty acids. You have the standard nomenclature again. This one, if you name the carboxyl group to be carbon 1 and alpha to the carbon next to it, like this one, carbon 1, that's carbon 1 to 18. You have octadecenoic acid, decene, because for 10 carbons you have deca, but since there's a double bond, you have decene. Since you have the carboxylic acid, you have the oic acid. For any carboxylic acid, we always end with oic acid. You have learned that in the organic chemistry. So octadecenoic acid, but we want to specify on where is this in. It is in carbon 9. So 9-octadecenoic acid, and if you want to specify whether it's cis or trans, we have to add cis. and we want to be very specific again, you have to indicate the number of carbons. You have 18 colon 1, and delta 9 indicates that there is a double bond on 9. And you can also have this. You have the icosapentaenoic acid here. Again, you have already indicated. So it's another way of naming. The second one we have here, followed by the superscript like this. No? Another way of naming, as I have mentioned, is katong, what we name as an omega. For polyunsaturated fatty acids, an alternative convention number the carbon in the opposite direction. So we name again from the opposite direction. Instead of here taking our carbon 1, we name from the tail, from the end. Now without the carboxyl group. And that is how we name, like 1, 2, 3. This one is an omega-3 fatty acid. So imagine there are a lot of omega-3 fatty acids, and we have to be very specific. That's why we have the Iupac have established this system of naming fatty acids to be very particular, very specific, and way of naming this the standard one. Okay, and for omega, way of naming it's very vague and very broad, no, because there could be a lot of omega-3 fatty acids. So this is designated as kaname, or should tell with the omega, the last letter in the Greek alphabet. And the positions of the double bond are indicated relative to the carbon. Here, you can see here, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, usually fatty acids, simple one, are even. Like you can have 12, 14, 16, 18, 20, 22, 24. Now they're usually even. And then they can have 1, 2, 3 double bonds or no double bonds at all. For unsaturated, of course, they expect to have a double bond. Okay, so like in this case, no, if we want to name this one using the omega, the old system of naming, you have carbon 1, 2, 3. On carbon 3, since we start numbering from the tail, call this one as an omega-3. And here, this is to indicate that the double bond is on the third carbon from the tail. Here, 1, 2, 3, 4, 5, 6. There's a double bond in carbon 6 from the tail position. This one, the hydrophobic end position. So you call this one as an omega-6. This is also an omega-6, an omega-6. But what is the difference? As I mentioned, this omega-6 way of naming is very, very broad, no? And you have to indicate how many number of carbons, like 14 colon 1, which means there are 14 carbons in one double bond. 18 2 omega-6, which means that there is 18 carbons and there are 2 double bonds. The first double bond is on carbon 6 from the tail end. You have also 23 omega-6 fatty acids. So you have here 20 carbons and 3 double bonds. The first double bond is on carbon 6 from the tail end. Okay, so if you want to be very specific, you would rather use the standard way of naming and start counting from here. It's very specific. But nevertheless, just know that there is a system that you have that. And in fact, even today, we're still using the omega system of naming our fatty acids, and that is what you will see on food labels, the omega-3, omega-6, and omega-3 fatty acids. So if, for example, some manufacturers would claim that they have the omega fatty acids, then you have, as you having been able to learn all this, then you have to check what kind of omega-3 fatty acids. And by then, having these differences in the double bond structure, like how many double bonds or the number of carbon atoms in the hydrocarbon chain length, it will affect on the melting point of our fatty acids, and it will affect on its properties. So would it be more liquidy, not liquidy? What would be its melting point? Okay, so these are some of the examples of the fatty acids. Again, you have the ALA, there are common names for that. Usually, you can find this sa mga gatas, DHA, EPA, ALA. You can find this. I think I have already mentioned this last time. So you just familiarize yourself with this one. Omega-3, 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 they have carbon 22, 6, double bonds. You see here that it's all cis. So omega-3, 1, 2, 3, 4, 5, 3, 4, 5, 6. Okay. So there are 6 double bonds for DHA, hexanoic acid, DHA, and then the F. These are the common fatty acids, omega-3 and omega-6 fatty acids that you can find on your food label. Okay, so maybe next meeting I'm gonna ask you like for the food products that you are using at home, maybe I'd ask you what omega fatty acids is being indicated, no, sa inyong food label for those who are claiming. I'm gonna ask you for that next meeting. Okay. But also, I think I have mentioned this. So yeah, so again, we have the head and tail. No, I have mentioned this one. The head is one without carboxyl group. You have the zero bond on. This becomes your tail. Okay. And you notice here that whenever there is a double bond present, no, it makes your fatty acid nonlinear. No, there will be kink. Conjugated. Okay, so it wouldn't be straight chain. So if, for example, this one is, you have too many saturated, you call this an unsaturated fatty acids, there's no double bond here in the structure. Expect this to have a lot of palmitic acid here, and you expect that there will be strong interaction again to the tail end of this palmitic acid, and with that, there will be a strong interaction, and with a strong interaction, you would expect the melting point to be high, you know? And because of the strong interaction, again, you expect the saturated fatty acid to be less fluidy and more solid at room temperature. Also this one. So this one, they only differ at the number of carbon chain. But with this, when there is a kink, when there is a double bond in the structure, for example, you can imagine this to be situated with another molecule of this oleic acid. No? If they are situated to each other, no, this kink would allow this chain to be a little far from the other chain of your oleic acid. And because of that, if there is a van der Waals interaction in this chain length, no, it will be lessened. No, it will be lessened because the distance, or if there is a kink, the distance between them is higher, and the van der Waals interaction will be weak. Okay, and also this one. Okay, expect that the more kink that you can see in the structure, then it will affect the lowering of the melting point of your fatty acids. And of course, you expect this one with the unsaturated fatty acids to be more liquidy. Now, you don't expect this one to be more of solid, but you expect this one to be more liquidy. And so you can only imagine when you have fats and oils at home, those that kanang matulog, no, you expect that one contains a lot of saturated fatty acids. Katong mga liquidy contain a lot of unsaturated fatty acids. So that will be your next task, no? I would like you to check on your oils and fats that you're using at home, and you can check on the label, or if it is indicated. Usually they don't indicate it, no, but what kind of oil are you usually using? Is it lard? No, is it lard? Is it corn oil? Is it sa pa may oil? Excuse me. Is it vegetable oil? No, vegetable oil. Is it vegetable oil? Is it corn oil? Usually sa gawas, they're using sunflower oil. Sa pa. Kanin sa mga beauty products na they're using jojoba oil, myristic oil. Okay. And so it contains actually a mixture of fatty acids. It's not just one. So we'll see later. Let's see here. And yeah, so we'll look at the structure. We'll look at later, I think, in one of the slides here that there are examples, no, of some products that would uh, that the fatty acids are indicated. Okay, so by the way, there are what we call as essential fatty acids. And the essential fatty acids, I have already mentioned this, is the fatty acid needed in the human body that must be obtained from dietary sources because it cannot be synthesized within the body. So it's also the same when we talk about essential amino acids. Our body needs it, but our system, our human body couldn't synthesize, and therefore you must get it from our diet. And that becomes our fatty acids or amino acids. If we're talking of amino acids to be essentials, in this case, we call this essential fatty acids because again, we need it in our diet. There are two essential fatty acids. We have the linoleic acid 18.2 and linolenic acid 18.3. I have already discussed this. There are usually the omega fatty acids. No? So you have the alpha linoleic fatty acids. You have here the function is structure and function of cell membranes. You have the retina of the eye and the CNS. We know this ones. Usually our source are fish. Cold water fish have higher omega-3 fatty acid concentration. So normally, for example, if you eat tuna, no, and there are actually some of the tuna products, canned tuna products that you can see in the supermarket would indicate no, they have the omega-3 fatty acid. And why would they really want to claim that one as part of their marketing strategy? Because these are one of the essential fatty acids now that is very important for functioning of our cell membranes and structures and our central nervous system and the retina of the eye. Okay, so another fatty acid, you have linoleic acid, 18.2, there are 18 carbons and 2 double bonds. So this is an omega-6, 1, 2, 3, 4, 5, 6. This is an omega-6 family fatty acids. And its function is for growth, skin integrity, fertility, and maintaining red blood cell structure. Okay, so if you want your skin, usually our source again here are vegetables and meat. And even this one, the fish, especially kanang mga oils no, from fishes, they also have a lot of fatty acids, the omega fatty acids, this case linolenic fatty acids. And it is one of the claim. Once you have that, lack of this rather, it can cause skin redness and irritation. It can affect skin integrity, fertility, maintaining our red blood cell structure. And of course, because of that, our source are vegetables and meat. And also, human breast milk have a higher percent of linoleic acid. And I think it's also one of the reasons why some those who can afford would rather want to have their skin treated with milk. And also you notice that if you really just have if you really eat properly like vegetables and meat, and you will notice that for those who are very diligent in eating good sources of food, vegetables and meat, you can see that there's that very nice skin, and there's a good skin skin structure, right? As really you compare for those who would eat less containing this essential fatty acids. Another fatty acid, you have the arachidonic fatty acid. It's an omega-6 fatty acid. It is synthesized from linoleic. So this is 20 carbons. This one is 18. So from 18 carbons can actually increase the number of carbons in our can synthesize this one from linoleic acid. So the function of this is precursor for the family of eicosanoids, which are oxygenated derivatives of this fatty acids. So what becomes this to be essential because this becomes a precursor to another kind of fatty acid, which is a complex one, not the simple one, which is the eicosanoids fatty acid. So what is the eicosanoids? Eicosanoids kaning mga inani, no? Prostaglandins, thromboxane, leukotriene. So there are hormone-like molecules present in cell, in red blood cells, transported in the bloodstream to their site of action, which further exerts their effects on the tissues. They are synthesized. So again, you have this example. And it is for this reason that there are hormone-like structures within the cellular system. They are also considered to be essential fatty acids. So why would it be important, icosanoids? Because they are part of blood clotting process. In fact, thromboxane A2 and prostacyclin, it stimulates the construction of blood vessels and platelet aggregation. We need this one, especially if your system, if our body is being attacked. For example, masamad ka, no? Di ba gina malikayan, no? We need the blood clotting process in our body to heal. Isod good, magsige na lang tag-clot, no? And God is good because He was able to have this mechanism where you have the blood clotting process. And imagine if we are masamad ta, no? And continuously mag-bleed ta. Okay? So, simba ko pala yun, no? And thankfully, we have this blood clotting mechanism. It allows platelet aggregation and stimulates construction of blood vessels to prevent too much blood loss. Okay, so masamad ka, blood clot na yun ang katong part of our body, no? Sorry, spine. So alternately, you can also have this inflammatory response in our body, and you have the prostaglandins, no? Especially if there is an infection, it will become our inflammatory response, no, as a sign that there is an invasion and our system or body can address. And also you have this important for the reproductive system. So if you want to be healthy, you always have to eat good meat, vegetables, and especially those sources of fatty acid. I remember when I was younger, no, and I think I was in high school, and I always have also kahit sa una, we have this katong squalene, no? Squalene. I can really, now looking back, I could really tell my skin really at that time was very, very nice. Na mga sinaw-sinaw, nga murag hamis kayo. So you can just imagine, no, kanang mga those that really eat well and have very, would intake good food. And this highly source of source of omega fatty acids, no, they really have very nice skin. So I can attest to that when I was young, no, but of course later takula na mainom og mga daghang mga imnonon for the body, and there will be a difference. But if you continuously maintain your system, eating nice food, dili mag diet, no, dili mag skip og mga pagkaon, okay, can actually would promote, no, a very good skin. Skin integrity. Okay, so also you can find this the icosanoids that would regulate processes in gastrointestinal tract. For example, prostaglandins can inhibit gastric secretion of protective mucus and inhibition of hormone-sensitive lipases. So this one are some of the biological processes. I think when you go to your biology, this process may also be mentioned. Kidneys also need prostaglandins. It dilates renal blood vessels, which results in increased water and electrolyte secretion. In respiratory tract, Leukotrienes also promotes the construction of bronchi, and prostaglandins promotes bronchilation. So in fact, if during the COVID time, if you eat a lot of this,